make sure you can see the TV. Okay.
Perfect. All right, quick review from Wednesday. Talk about signed area.
Yep.
So area above the x-axis counts as
Positive.
and then area below the x-axis counts as
Negative.
negative. Good, and then what's the difference between net area, total area?
Total, I'll just say what I said in my thing. The total area tells you how much change, but the net area tells you where that change actually got you.
Yes. Yes, I did really like that phrase that you had in your homework. That works really well. It was pretty much exactly what you just said, where the total area tells you, how'd you say it again? How much change.
How much change.
Yeah, how much change happened, but then the net area tells you how far that change got you in the end. Yeah, good. I like that. That's a good description. Okay, then we did some examples with just some geometric shapes. That's what your homework was about too, was some just geometry to find the area under curves. I just want to really solidify this idea. And so we're going to talk about, we ended the day with this, that your signed area is your net change, your total area is your total change, ignoring the sign. So the integral is the limit of a sum of rectangles. We talked about that on Monday. Remember that one? Mm-hmm. Okay. I'm going to give you another little phrase of what the integral is. Another way that we can think about the integral that's equally as true is the integral is the accumulated change from a rate.
Accumulated change from a rate.
We're going to solidify that idea here all day today. Well, maybe half the day today, and then we're moving to the next idea, but we are going to solidify this statement. I'm going to tell you that the integral is the accumulated change from a rate. On Wednesday, we made the important shift from exploring the area problem using signed area from just like total area. We were saying that calculus chooses accumulation, and so we're going to choose that. But the signed area isn't the deepest that these ideas go. Signed area is really just a way to measure accumulated change. So accumulated change from a rate is what the integral really is. So the simplest accumulation story that there is that of a constant rate. So here is a constant rate, and I'll say v of t equals 3, and I'm interested from 0 to 4 is what I'm interested in right now. So we can just think about this, like how far would someone travel if they had a constant velocity of 3 feet per second for 4 seconds? How far would they travel? 12
feet.
Okay, that one's really easy, right?
Mm-hmm.
Okay, now, how did you find that it was 12?
I mean, you can do the area. I mean, if you like think about like with the graph, you can put the line up from 4 all the way up to your v of t graph, and you have a square. You can find the area of that, so it's side times side, so it's 12.
Okay, so you're connecting right away that we have this area here. Good. So here's this area under this curve, and the area is literally the multiplication of what you did to find after 4 seconds, how far will they be? 12 feet, right? And so that multiplication is literally the area. You've got the 3 here, you've got the 4 here, you've got the 3 here. 3 times 4 makes 12. Okay, so one way we could write this, I don't think I want to write it like that. Yeah, I will write it like this. The change in position is equal to the velocity times the time. The change in position equals the velocity times time. Does this make sense?
Yeah.
Intuitively, pretty straightforward. Nothing really groundbreaking here. Just a little bit of notation. Okay? And the units prove the meaning, right? If you have feet per second for velocity, and then you have times seconds, that'll equal your feet, which is what your position better be in, right? Okay, so that's the simplest type of accumulation story. And so what I want to point out here is that, okay, I could have asked you about any interval though. After 1 second, how much change is accumulated?
3.
3. After 2 seconds, how much change is accumulated?
6.
Right, and we can keep going. So this is what my point is to say, is that the integral is the accumulated change from a rate. Is because here's my rate of change, constant 3, but that's my rate of change. The accumulated change is this area under the curve. Okay, so we're kind of connecting these ideas together. Okay, there's another example here. This is also a velocity graph. You got your t-axis in seconds. You have your feet per second again. V of t equals x. So there's your line over 0 to 6.
In 6 seconds.
So what is the displacement?
18.
Okay, how'd you compute that?
Area of the triangle. So 6 times 6 is 36, divided by 2 is 18.
There you go. Okay. So you imagined this triangle. This represents the accumulated change over this time. What does, I'm not gonna say. Okay, so 18 feet, right? That's pretty easy. All right, this stuff's pretty easy, but we just want to make a connection here because now we have something like this. Now we have a velocity graph that's curved and not a straight line. So we want to estimate displacement with this velocity graph. How could we estimate the displacement?
Rectangles.
Yes, we want to use rectangles. So this is the idea of the integral. We use rectangles to when the rate of change is changing. The rate is constantly changing. He's going faster and faster, then he's going slower and slower. Here, he was constantly getting faster and faster. Here, he was just staying at the same, cruise control was set. But here, we're traveling in one direction the whole time, but we go faster and faster, and then we slow back down. Because this is a velocity graph. Okay, let's estimate the area using 2 rectangles over 0 to 8. And we're going to use 2 right endpoint rectangles. So let's talk about that. So if we have 2 right endpoint rectangles, the right endpoint means that we want the top right corner of the rectangle to be on the graph. So if I make an even interval between 0 and 8, then I'm going to have 4. So my right endpoint for my rectangle is going to come up at 4 and and then go to 0, and then there you go. Does that make sense? Okay, and then my other rectangle, the right endpoint, where will that be?
8?
Yeah, 8. Dude, there's my right endpoint. So where's my other rectangle?
I don't know.
The other side?
Yeah, because I'm using 2 right endpoint rectangles, so like, what do I do here? Because
What?
that's how high the rectangle is. Actually doesn't have any height, so now what do I do? Well, I guess I only have weirdly one rectangle to estimate, so I guess let's estimate that.
Can't you do left point and one left right?
I could, but then I would be having a left and a right, and I've asked you to use 2 right endpoints.
Oh.
So then you would be disobedient.
16 times 4 is 32 times.
Well, you're just gonna be really inaccurate with 2 rectangles.
64.
Okay, so we'll just have to take this estimate of 64, because this is 64, because my other right endpoint is right here. So it doesn't have any height, so I can move the line over, but then like what? There's no area there. See what I'm saying? Okay, it's a little bit easier to see when we use 4 right endpoint rectangles.
Yeah.
Okay, so let's do 4 right endpoint rectangles. I'm not gonna be able to erase that blue line because it's on the white line. That's okay. Okay, 4 right endpoint rectangles. I'm gonna split this into 4 equal size intervals if I'm using 4 rectangles. So from 2, the right endpoint needs to go on the graph and then over. And then this one would have the right endpoint on the graph and then over. This one would have its right endpoint on the graph and then over. And this one will have its right endpoint on the graph and then over. See again where that happens again?
Yeah.
So my 4th rectangle, where is it? Well, it's not there.
Yeah.
So I guess I'll just estimate using these 3 now. Because the right endpoint is 0.
Wait, but how do you know where the what the y value is of the 2 ones that are at 16?
I don't know. I guess we'll just have to estimate.
12.
Sure, that looks like it's about 12. Okay. So now we have 2 times 12.
24.
Okay.
So 48 plus 64. Wait, what?
Mm-hmm.
Yeah. 48 plus. Oh wait, no.
This will be 2 times 16.
So it'd be 48 plus 32.
48. Oh,
48
because you're
is between
doing,
the 2 of them, yeah.
24 here, 24 here. And then what was this?
32.
32. Okay?
So it'd be 80.
80. Mm-hmm. Right. Okay, so then we have about 80. Okay, what did we say the first one was?
The first one was 64.
64? Okay. Okay, which one's probably more accurate?
Probably 80.
Probably 80. Yep, that's probably more accurate here. Okay? Do you see how we can sometimes run into some trouble with using a right endpoint or a left endpoint? What if we used a left endpoint?
It'd just be the same thing on the opposite.
Yeah, I'd end up having the left endpoint right here, and then I'd have 3 rectangles over this way. I could do that. It's probably gonna give me the exact same estimate.
Yeah.
Okay. Because this is a velocity graph in green, what does each rectangle represent physically?
Feet move. I mean displacement. Wait, no, not displacement. Distance traveled.
Okay, yeah, distance traveled. Yep, good. In this case, displacement would end up being the same
Yeah.
because we're all positive here. But yes. So you could say the change in position,
Yeah.
in other words. And really you could say it's the change in position during that time slice. Right?
Yeah.
So if we're estimating just from 0 to 2, then the change in position from 0 to 2 would be 24. Right? Makes
Yeah.
sense? Okay. All right, so if we continued the graph into the negatives and the velocity becomes negative, what happens to the rectangle and what does that represent?
Distance traveled. Negative distance traveled.
So like if you added something like this, what would that rectangle represent?
Wait, what?
It'd be distance traveled still, but it'd be in the opposite direction.
Mm-hmm.
Or just like a different direction.
Like you could say like negative distance in a certain direction.
It's in whatever direction is closer to your starting point, so 0. If you're thinking about it like on a map.
Yeah.
Right.
It's like distance traveled south instead of north.
Sure, yes, distance traveled south instead of north, or east instead of west, or whatever you want to say, depending on whatever you said your starting point was, and whatever you said positive direction was. Yeah, it's still the change in position during that time slice, right?
Yeah.
Even though it's negative, all that means is that it contributes negative change. Okay? So it's still a change in position over that time slice. Okay, yeah, you guys are fine with this. Okay, good. So I just really wanted to hammer this home, and all of this goes to say, here's the big ideas. I want you to copy this down and have it in your notes so you have it. The big idea with all of this is that f of x, if f of x is a rate of change of some quantity f, then I need to still finish this sentence. The net change in f equals, how do you think I would finish this? Curious to know what you might say.
Displacement.
Okay, I want to make it more general, because we don't always have velocity graphs. Sometimes we have other kinds of graphs. So that would be true.
Oh, area.
Area.
Under f of x.
Yes, good. Area under f of x. Okay? That's really the big idea of this whole next 3 weeks. The next 3 weeks are all about this. Your net change in f is going to be the area under f of x.
Mm-hmm.
So if you had velocity is the rate of change, what is velocity the rate of change of?
Speed and time.
Wait.
Time.
Not time.
Distance and time.
Speed. Yeah, it's the rate. Wait, no, it's not the rate of change. It's the rate of change in displacement. Oh, rate of change of position.
Yeah, velocity is your rate of change of your position. If you've got a velocity, what's changing?
Your position.
Your position better be changing. Your speed may or may not be changing, even if you have velocity.
Yeah.
Like that very first example we just did today, constant velocity, I have no acceleration. But my position is definitely changing. So if v of t is the rate of change of position, that would be like your net displacement. Okay? All right. A of t, or acceleration for A, is the rate of change of what? Let me think. If your acceleration is changing, speed is another word for acceleration.
Velocity.
Yes, your velocity will be changing if your acceleration is changing. So A of t, or acceleration of t, is the rate of change of velocity. Okay? So generally, f prime of t is the rate of change of, definitely know this one. Don't
Time.
overthink it. Don't overthink it.
Time. Speed.
We got some function, f prime. rate of
Oh,
change
f
of
of
f of x, right? That's literally the definition. It is basically a trick question, okay? So f prime of t is the rate of change of f of x. That is your net change in f. Okay? So there's your big idea. The integral measures accumulated change. That's what the integral is. It measures accumulated change. We often estimate it using the rectangles, but the area under a curve is accumulated change. The area under a curve is accumulated change. Okay?
Yeah.
Okay. So we have all these intro ideas, and we're still only estimating. Okay? We don't have this formalized yet, but we have to really make sure we know what it is we're trying to figure out. So what we're going to do is we're going to start formalizing this. Okay? We're going to formalize our rectangle method and actually start computing some real areas under curves. So this is like changing to a new topic now at this point. So if you want to write a new topic or however you're keeping your notes, we're talking about Riemann sums.
Riemann.
Riemann sums. I love Riemann sums. This is so fun. Riemann sums are so great.
Your excitement makes me excited.
Okay, I'm so glad.
Well, it makes me
Maybe you'll like Riemann sums too by the time we're done.
Riemann. It sounds fun. Riemann.
You know,
What's going to be funny is you actually are probably all going to hate Riemann sums by the time we're done, but it's fine. It's okay. I love Riemann sums, and I think they're great, but...
What if will we still love them if we don't learn about them?
I don't know. We'll see.
Riemann.
I just think this is a really amazing method. Okay, so some history. So Newton, Leibniz, they discovered calculus and created kind of the beginning principles. And they definitely talked a lot about the tangent line problem and really took care of that one. They started talking about integrals and they had the ideas of integrals, but they did not really get that formalized before their time was up. So we've taken calculus out of their hands and said, we've got this.
We got this.
And Riemann is one of the people who took integrals and was like, I've got this. And he figured it out. So I've copied this graph that we had from before. This is just a copy of what we had from Monday. And so just some quick refreshers on it. What's the width of each rectangle?
B minus A over 3. Sorry, 4.
Yeah, b minus a over 4. And the 4 is telling us what specifically in this case? Like, why did we pick 4? What's the 4? What does the 4 mean?
Well, there are 4 rectangles, so you have to take that width of the rectangle, which is b minus a, and then you have to divide by 4, which is the number of rectangles, and that'll get you whatever that area is.
Yeah, so you'll always have b minus a, whatever the interval we're talking about is, divided by the number of rectangles that you have. In this case, it's 4, but we can just use n to talk about it generally. However many rectangles you decided to split it up into, that's what that bottom number will be, okay? All right, this is a review. Remember I told you I'm writing this change in x as a shorthand of that fraction. We'll come back around to that today, but especially next week we'll come back around to that. And so what's the height of each rectangle?
of A.
Okay, f of a is one of them. But in general, it'll be,
F of X.
yeah, f of x wherever we're at. So I'll just say like x sub I to be like whichever rectangle we're talking about. That would be the height of the rectangle, right? Okay. So the area of each rectangle would be there's your height, there's your base. So the area of each rectangle is
Delta X times F of XI.
okay. That looks like a pretty scary expression, but it literally just means base times height, right? What is the total area for this figure in general?
F of X1 delta X plus F of X2 delta X plus F of X3 delta X F of X4 delta X.
Good. Good. So that would be a great one for this situation. And then notice anything about this that we could simplify?
Delta X times F of X 1.
That's it.
Plus f of x2 plus f of x3 continue. So you could put
I would just write
What's
F
it?
of X n at the end.
what's it called? The explanation one.
Oh, that's a factorial.
You could put a factorial for the x.
Actually, you can't.
No.
And actually, we're just about to get to what you can use instead of a factorial. We're like 10 seconds away from it. A factorial is continued multiplication. So if I wrote 4 factorial, that would be 1 times 2 times 3 times 4. So that's multiplication when you use a factorial. Unfortunately, we don't get into factorials in calculus, but instead we use a different notation. Okay, remember what does delta x equal?
B minus A over N.
B minus a over n. So we could substitute that if we want to. Again, we don't have to, but we could if we want to, just to see it. I'm just going to put it there for visual sake. Okay, this is what we call a Riemann sum. This is a Riemann sum. Okay, but there are a couple of things just to show you real quick before I can show you the actual Riemann sum formulas in all their glory. The first thing is what we call summation notation.
I don't like that.
Summation.
Doesn't it kind of rhyme?
Sounds like a rapper name or something.
Summation notation? Yeah.
Summation.
That would be a great rapper
It's
name.
your boy. Summation.
It's your boy.
I love that. I'm saving that for later. Okay. So if we wanted to write out the sum of all the numbers from 1 to 100, I could just keep going, right? 2, 100. Okay, if I wanted to write out that sum, I don't want to write out that sum.
No.
So instead, this is what we use as mathematicians in terms of notation instead of writing them all out. We use this.
Oh.
You've seen this symbol?
Yeah.
Yes, you've probably just seen it in passing or online or something. I'm gonna try to make that a little more accurate. This is a Greek letter, sigma,
Ah!
not theta. What's theta?
Oh, theta is squiggle.
There you go, there's theta. This one's sigma. We use sigma to represent sum. This symbol means sum. That's all it means. It looks scary, it looks fancy. It looks like we're supposed to do something with it. It looks like it's supposed to mean something very complicated. It literally means sum. So if I wanted to write out the sum from 1 to 100, this is how I would use it. I would write this symbol, sigma. I would write I for index equals 1 to 100. And then inside of it, kind of like a function, I would need to write this I. So let me break this down. What this means is I'm taking the sum of I. I could replace I with X, but we typically use I because it stands for index. And it's like, as you keep going, it's like, oh, I'm at index 3. That means I'm at the third number. Okay, I'm at index 4. I'm summing the fourth number. I'm at index 5. I've added now the fifth number. Like, it just keeps going. So I use I for index. So we're just using I, say the sum of the numbers from 1 to 100. That's what that means. Make sense?
Yes.
Okay. Let's just practice one or two real quick of interpreting what they could mean. And then let's actually do one. Let's do, I'll just make one up. Let's see. Come on now. Right. There we go. I'll use K this time because I can. We could use I, but I'll just do K from 1 to 6 of the square numbers minus 1. So I want to add all of the numbers, the square number minus 1 numbers. And I want to add it for the first 6 of them. So let's break this down. What would the first one be?
1 squared minus 1.
1 squared minus 1, so I'll write 1 squared minus 1. Plus, because this means sum, plus
2 squared minus 1.
2 squared minus 1,
3
plus
squared minus 1. 4 squared minus 1. Maybe 5 squared minus 1.
and I go to 6.
And stop.
So I put in 1, I put in now 2 is the next one, 3, put in 4, put in 5, and then I put in 6, and then I stop there. Okay? Alright, I think we could probably do this mentally, but what is it? 0 plus 3.
4. 3.
0 plus 3 plus 8 plus
15.
11. Oh, yeah.
24. 35.
Okay. 3 plus 8 is 11, plus 15.
26. 40. Sorry, 51. 86.
Alright, so the sum of the square numbers minus 1 from 1 to 6 is what? What did you say?
86.
86. There you go. Oh! Not too bad, huh? It looks kind of scary when you look at this. You're like, what in the world does that mean? And you're like, oh, it just means sum. I'm adding the square numbers minus 1 6 times. Okay, you could also start at,
Do you have to do this manually every single time?
yep. So,
Wait, really? Even if you're adding.
well, there's actually a few special ones that we'll look at next week, but
Oh.
let's see. I just want to also show you that you could start at 0. So if I have indexes 0 to 10 of, I don't know, the cubed numbers. There you go. So now I have I cubed. Let's just talk about this. So my index is 0 to start. Is that fine? Sure, I would just plug in 0 the first time. In this case, that won't add anything to my sum. If I had it like this, then it would add 1 to my sum. Could I start my index at a negative number? Would that be a problem?
No.
Yeah, actually not really. I would just need to plug in 2, or -2, plug in -2, then plug in -1, then plug in 0, then plug in 1, and keep going all the way up to 10, and then add it all up. Okay? So, now that we've talked about this notation, this is called summation notation or sigma notation. I like summation notation because it sounds way more fun.
Summation.
So, for calculating integrals, back to what we're talking about, just like we were doing with our rectangles, we want to add up the sum of all those rectangles, right? Now we could just use some shorthand to do like 10 rectangles without needing to write out every single one of those.
No way.
Does that make sense?
No.
It saved us a lot of writing, for
This
sure.
is sick.
Does that make sense? You see where that's going?
This is kind of cool.
I don't have this
This is
pen.
kinda cool.
It's doing
Yeah. What? Okay, so there are 4 different flavors of Riemann sums.
Riemann.
Okay, I'll show you the first one. Don't panic. It looks scary. Here it is.
Ah!
This is the first Riemann sum out of 4. I haven't read the other ones yet, because I'll write them next. But
What does RN stand for?
good question. R stands for right. L stands for left. I'll tell you the others later. There are right Riemann sums. There are left Riemann sums. There are 4 total flavors of Riemann sums, and the other 2 I'm going to get to in a few minutes. But this is the right Riemann sum. Copy this down exactly as you see it. Okay, it looks scary, but let's break it down. This is what it's going to mean.
Delta X. The sum from the first one, however many you have, of f of the first one, your starting point, plus the base of each of your rectangles times I.
Good, you're good. That was good interpreting work. We just need to put some of those last pieces together to really get it. Okay? So I think I wrote it, I wrote it down here again so that I could annotate it. So here, what does it mean? Okay? So this, what does that represent?
Base of your rectangle.
Yes, there you go. That is the width of your rectangle or the base of your rectangle. So width of rectangle. Okay? And then this whole thing represents the heights of your rectangles.
Huh. Oh, so it literally just means base times heights.
It's literally base times the sum of the heights.
Literally.
Okay? But I'll break down the pieces on the inside too. Okay? So you have the width times the height here is really all you have. So there's the width of your rectangle. Now this is right here. That is the sum, right?
Yep. From 1 to however many you have.
Of the heights of however many you have. This A.
Oh, so your starting point, plus however many bases you have over.
That's good. Very good. So this is your y value or the height of your initial shift. Let's see. No. All right. I want to do it like this. This f is the y value. That's what that means, right?
Yeah.
Okay. Or in other words, the height of. Yes.
Yep.
And then the a is your initial shift. So maybe you start at 0. Maybe your interval is from 0 to 8. So maybe a is 0.
Mm-hmm.
Well, great. Then you just put in 0 there plus whatever. It doesn't matter. Or maybe your interval is from 3 to 10. Well, now you've shifted your starting spot to 3. So you need to start there. Okay? And then this is plus the width of whichever rectangle we're at when we're summing.
Yeah.
Okay, does that make sense?
Yeah.
Okay, so visually, like if I go back up to here and you have the Riemann sum in front of you, visually this is what we're doing. We're saying the base of the rectangle times the height, which would be f of a, and times whatever rectangle we're at. Now, this is a right Riemann sum that you've written down in front of you. So then that means the right endpoint would be the one on the axis. So we would need to have f of a, this distance, plus this distance to get that height. Right? I need that f value. Then the next rectangle that I would sum up, I need the shift of a plus the width of this rectangle plus the width of this rectangle for that right endpoint rectangle. So I need that f value. So that's how this works. That's how we get this, is because we need to say, well, I need to start wherever I started, and then I need to add the width of each rectangle as I go along. Okay?
Yes.
Okay, so here are the other ones. I want you to copy them down exactly as you see them. They differ from each other just slightly, but we're going to break it down as much as we can before we run out of time. A left Riemann sum is b minus a over n, which is the width, times the sum of I equals 0 to n minus 1 of f of a plus b minus a over n times I.
Who comes up with these?
Riemann,
Riemann.
How do you do that?
of course. It's not too crazy to think about. I mean, you could come up with this yourself. I could have spent a time for us to build these, and I considered doing that. But I was like, I think we can just show it and understand it. Because I could have said, okay, well, we need the sum of all these heights, and how could we represent this distance and whatever. And I could have asked you all those questions to figure out, oh, we're going to need the initial shift plus whatever rectangle we're at, find that f value, and then I need to sum that up however many times I need to do it. Oh, by the way, we could have done it ourselves. Okay.
Sometimes I wonder what it would look like if you could like go into the brains of Euler or this dude.
Riemann. Yeah,
Numbers anyway.
that would be pretty awesome. Okay, m sub n is b minus a over n. Actually, before we keep going, what are the main differences between right and left?
It's n minus 1 on top, and it's equals 0, which I don't know why you put it at 0. Doesn't really do anything.
Yeah, so we need to think about that. So here's a left Riemann sum in this picture. I have the left endpoint on here. Okay. If I start at I equals 0, what would happen to the b minus a times I term?
It would cancel out.
Yes, it would just cancel it out and it would be 0. N minus 1, I equals 0, f of a plus, plus b minus a over n times I. Okay. So if I start at 0 for I, then this goes away and it would just leave me with a, whatever we started at. So then I would have this distance plus 0. Great, and then I'll take that f value, and there it is.
Oh.
Does that make sense?
Yeah.
And then the next one would be n equals 1. So then I would, or I equals 1, sorry. Then I would have a, the distance a, plus 1 width of a rectangle. So then I would have the distance a plus 1 width of the rectangle, that f value.
Isn't, separate question, isn't I an imaginary number in that?
Yes, so that's actually why most of the time we use k instead of I. But in calculus, you tend to use I more than K, but once you do outside of calculus, you use K here, usually, instead of I. I don't care what one we use, I don't care which one you use, as long as you just pick one and it's consistent, like within a problem. And then, yeah, you could pick X, it doesn't really matter, it's just a variable, but we usually use K or N.
I feel like I'd be liable to times the binary difference.
Yeah, that's valid. So if you want to switch to K, that's great. The Riemann sums officially have an I in their like formula, but whatever. Okay.
Goofy math people.
Great, so that's why the left is a little different from the right, is because it depends on which endpoint you're talking about and what F value you need. Okay, here's the M sub N, so you have B minus A over N. All right, let's just copy these down and then we'll call it a day. 0 to the N minus 1 of F of A plus B minus A over 2N plus B minus A over N times I. There you go. Okay, well, we don't have time to go over it, so go home and think about it. What does this mean? And why is it there? See if you can maybe come up with what it might mean. So here I'll tell you, M stands for midpoint.
I could have guessed that.
Okay, you could have guessed that. That's your midpoint Riemann sum. Go home and think about why those pieces are the way they are. The T sub N is super easy. It is actually R sub N plus L sub N over 2.
What does T stand for?
T stands for trapezoid.
They have one for everything.
There is a right sum, a left sum, a midpoint sum, and a trapezoid sum. Okay, your homework this weekend is to just think about what these might look like or what they might mean, and then that's what we're gonna start with on Monday. Cool?
Cool beans.
Thanks. All right, this is gonna be so fun on Monday.